Hello, everyone, and welcome to today's NSERC PermafrostNet seminar. I would like to introduce today's speaker. Khatereh Roghangar holds a PhD in geotechnical engineering from the University of Calgary, where she focused on the probabilistic analysis of thaw settlement and infrastructure serviceability in permafrost regions under climate change. She has industry experience with BGC Engineering and National Research Council of Canada, and has published extensively on permafrost modeling and cold region geotechnics. Khatereh is passionate about advancing climate-resilient infrastructure design in northern environments. So, whenever you're ready.
So, hello everyone, I am Khatereh Roghangar and I have a PhD from the University of Calgary. I have just defended my PhD 3 weeks ago. And today I'm going to present a summary of my PhD. Today I'm presenting the probabilistic assessment of thaw settlement in permafrost terrain under climate change. So today I'm going to talk about an introduction, the deterministic analysis that we have done in this study, the probabilistic methodology that we have developed, and the applications of the probabilistic methodology that we have done, which are on the Hudson Bay Railway and the Inuvik Tuktoyaktuk Highway embankments. Okay, introduction. So, as you know, permafrost refers to the soil or rock which remains below 0 degree for at least 2 consecutive years. And because this is a thermal state of the ground, the climate change is causing the permafrost degradation. And there are many embankments built on permafrost, so this permafrost degradation is causing the embankments to be unstable. And one of the problems that is happening for the embankments is the thaw settlement. Thaw settlement is the most common hazard in cold region infrastructure, and deterministic analysis does not capture the uncertainty, and they just give you a single outcome instead of a range, and the uncertainty in soil properties and climate scenarios needs to be incorporated. And that's why we have defined our main objective and problem statement to develop a probabilistic methodology to assess thaw settlement under the climate change. But to do this big objective, we have defined a couple of sub-objectives, which one of them is evaluating the climate impact on embankments in permafrost regions. The other one is to integrate probabilistic analysis with thermal modeling, and then apply the methodology to the linear infrastructure, which are the railway and highway, and then to assess the serviceability and optimize the maintenance strategies. But before jumping to any analysis, I should clearly mention that we have calculated thaw settlement using the formula that you can see. So thaw settlement is the thaw strain times the thaw layer depth change. And we have got the thaw strain from the empirical equations that are in the literature, so from Nelson, Ladany, or Spear, and we have calculated the thaw layer depth change from the thermal modeling that we have done using the TEMP software. And now let's talk about the deterministic analysis that we have done. So we have chosen 3 study sites on the Hudson Bay Railway corridor. And the first one was Churchill, which is located in the continuous permafrost. The second one was the Charlevoix, which is in the extensive discontinuous permafrost. And the third one was the CPUS in a sporadic extensive permafrost. So to do the analysis, we have chosen 3 different climate scenarios from the CMIP5. So we've chosen RCP 2.6, 4.5, and 8.5. And what you are looking at here is the air temperature that we have used for the thermal analysis. So the red dots are the historical temperature, and the others are the RCP 2.6, 4.5, and 8.5 from the top for Churchill Station, Charlevoix, and then the CPUS station. As I mentioned, we have done the thermal modeling using TEMP from GeoStudio package, we have used 5 different types of homogeneous soil columns, and we have gotten the soil properties from EBA reports and the literature that we had. And for each site study, we had one initial temperature at the beginning of the thermal analysis, and the boundary conditions were the N factor and air temperature at the top and the constant heat flux at the bottom and at the sides of the soil columns. And here you can see a part of our results. So at the left, you're looking at the Thaw layer depths, and at the right, you're looking at the Thaw settlement results for different types of soils. So this one is for sandy soils, this one is for silty sand, and this one is for silty soils. The rest, the silty clay and clay, because it would have been too small of a figure, I didn't put them here. But what you're looking at is that the blue color is for the Churchill station in the continuous permafrost. The green one is for Charbois in the extensive discontinuous, and the red one is for Sibiwesk, which was in the sporadic discontinuous permafrost. And the shapes are different climate scenarios, as you can see by the legend here. But it's important to know that you can see the minimum changes in continuous permafrost because of the colder climate for now and for the future, and the permafrost disappearance in some of the cases in a sporadic discontinuous permafrost. But let's jump into our main contribution, which was developing the probabilistic methodology. But what was the main principle of what we have developed? It was integrated probabilistic thermal modeling to predict Thaw settlement and the serviceability of the embankment. So we have done the probabilistic analysis using the Monte Carlo simulation as solver, and we have done the thermal modeling using TEMP. But what is Monte Carlo simulation? Monte Carlo simulation is a computational technique that can be used to study systems that include uncertainty or randomness. There are a couple of steps to do Monte Carlo simulation. First of all, you should identify your components, and then you should define your parameters. They could be deterministic or probabilistic. It totally depends on your problem and your data that you have. And then for the probabilistic parameters, you should get samples from their distributions that you've previously assigned and defined based on, again, the data that you have and your assumptions. You are going to randomly generate the parameters. You should run your simulations and then repeat the process for the other iterations. And the number of the Monte Carlo simulations, again, totally depends on you and your problem that you're looking at. So to do this integrated probabilistic thermal modeling, we have developed a custom Python tool that performs the Monte Carlo simulation. It automates the input generation for thermal modeling, or the TEMP. It calculates the Thaw settlement after doing the TEMP analysis, and then it assesses the long-term serviceability of each embankment, and it optimizes grading intervals based on the performance thresholds. But let's look at a detailed flowchart of the serviceability assessment tool that we have developed. As I mentioned, in a Monte Carlo simulation, you should first identify your components, you should define your parameters. In our case, these components are the soil properties. So step 1 of the serviceability assessment was to define the soil properties. The soil properties could be randomly generated based on the distributions that we have assigned for them. So moisture content and dry density were randomly generated at the first step, and then the particle diameter of the soil was also randomly generated. And then we had a couple of soil properties that were calculated based on the random generated parameters, such as the unfrozen water content and the saturation, bulk density, thermal properties, and the Thaw stream. So the check for saturation was to make sure that we have a physically possible soil column. Now that we have defined our soil column, it's time to define the boundary conditions. So as I mentioned, we had n factors at the top. So we have again randomly generated n factors for each iteration. We have gathered our projected air temperature based on the study site that we are looking at. We have selected the geothermal heat flux. The geothermal heat flux was a deterministic parameter in our analysis. And now that we have our soil properties, our boundary conditions, it's time to run TEMP-W in step 3. After running TEMP-W, it's time to extract the thaw layer depths from its results, and using the thaw layer depths and the thaw strain that we had in step 1, now we can calculate thaw settlement of the soil in step 4. So to do the serviceability assessment, we should define a criteria for thaw settlement to know what are we defining and saying that is serviceable, and if our thaw settlement that we've calculated for the embankment was less than the criteria, so we can consider the embankment serviceable at that time. But if the thaw settlement of the embankment is more than the criteria, we are going to consider it non-serviceable. And after 1,000 iterations, now we have the serviceability vector and calculated for the embankment that we're looking at, and this is the end of the process of the serviceability assessment. But another important part was the optimization method that we've developed. So at the start, you should set your thaw settlement criteria, as I mentioned before, and also your serviceability criteria. For example, you want to have 70% serviceability, and it means that you are going to have your embankment to be serviceable 70% at time. After calculating the serviceability and comparing the serviceability with your criteria, it's time for you to decide whether you should need grading or regrading your embankment or not. So if the serviceability of your embankment was more than your serviceability criteria, you don't need any grading. But if it was less, you should grade for X years, and X is defined based on your project. You can, for example, it could be 20 or 15 or something. And then you should again calculate the serviceability and compare it with the criteria. After finding all of the serviceabilities for each year where more than criteria, you're done and you have a number for the optimized grading interval. So to wrap up what we have done, I can say that we have developed this integrated methodology that does permafrost thermal modeling. It integrates Monte Carlo simulations for uncertainty quantification, and then probabilistic serviceability analysis and optimization of grading interval. But what's novel? What is new about what we have done? The probabilistic analysis and TEMP-W combination is new. The systematic application to embankment thaw settlement in permafrost, again, this is new, and the time-based serviceability optimization usage. But now let's look at the first application of our methodology, which was on the Hudson Bay Railway embankments. So again, you're looking at the modeling details. We had one homogeneous soil column with random generated soil types. We have gotten again the soil properties from EBA reports and literature, which are the averages of what we have defined, and then we've assigned a random like a distribution for them based on the standard deviations that we've found in literature. We had 4 initial temperature conditions, which represented different active layer thicknesses at the beginning, which were 0.5, 1, 1.5, and 2 meters. And the boundary condition was the same as the deterministic analysis. The difference was that the N factor was randomly generated at this time. And because we had access to CMIP6 climate scenarios, we have used SSP5 8.5 climate scenario. So based on different conditions, we have done 7,000 TEMP-W simulations for different scenarios. And here is a part of our results, the variability comparison between the results. So we had the Thaw layer depths or TLD and Thaw settlement or the settlement as the results. What you're looking at top is the histogram of TLD and settlement for the year 2100. And at the bottom, you're looking at the CDF or cumulative density function of these two parameters. What is obvious here is that the wider histogram for Thaw layer depths and the steeper CDF plot for settlement. But what does it show? It means that we have more variability in TLD predictions. And this is because the Thaw settlement that we have calculated is a fraction of the Thaw layer depths that we had from the TEMP-W results. But more variability in TLD prediction means that we are going to face higher risk of under-design or over-design, wider range of possible ground behavior, and greater sensitivity to surface conditions, which is really important for engineering practice. And another important part of our results is the histogram and CDF plots of TLD at the left and the Thaw settlement at the right of the slides for different years. So the red one is for 2050, the green is for 2070, and the blue is for 2100. But what is again obvious here is the variability is increasing over time. So the histograms of the 2100 results for both of the outcomes are much wider, and the CDF plus is less steep. But this growing uncertainty, what is its implication in the performance of the embankments? It means that we are going to require adaptive design and maintenance strategies to be able to keep up with the climate change and the variability that is increasing by time. And now let's look at the second application, which was on the Inuvik Tuktoyaktuk Highway embankments. So what you can see in the figure is a map of the Inuvik Tuktoyaktuk Highway, and the purple dots are the boreholes that we have used to do our study. So we had 10 boreholes along the ITH corridor, and the mean annual ground temperature at the study sites were between minus 6.5 to minus 30 degrees Celsius in 2017, which is the year that the ITH opened, and we have started analysis from that time. The embankment thickness was an important factor here. It varied from 0.9 to 4.6 meters in different boreholes, and we have done 1,000 simulations for each borehole location. So in total, we have done 10,000 simulations. What you're looking at here is an important result. So you're looking in the y-axis at the differential TLD prediction. Differential TLD means the Thaw layer depths at the year that we had in, for example, 20, 30, 50, or 70, minus the initial Thaw layer depths at the beginning of the analysis. So first of all, I should mention that we've categorized the results based on the field height. So the blue colors that you are looking at in this figure are the thin embankments that had less than 2 meters field height, and the orange ones are the thick embankments that had more than 2 meters of field height. But what is obvious here is that most of the thin embankments, except for the ITH 13, have a jump in the both magnitude and the variability of the differential TLD predicted by the year 2070. And it's really important. It's showing the significant effect of the field height not only on the magnitude but also on the variability of the predictions. It's important because it supports the need to incorporate embankment thickness as a key parameter in design. So if you have designed your embankment to be, for example, 2 meters and you ran out of money, you may save money at the time of the construction by reducing the field height, but it will cost you more in the future. And now let's talk about the serviceability assessment that we have done. So we needed a criteria to compare our serviceability and our Thaw settlement to be valid at this part. But I should mention that serviceability in this study is a pavement's ability to perform its function, which is providing a smooth, durable surface that ensures right quality, structural integrity, and safety. So we found the International Roughness Index, or IRI, which is a widely used metric for quantifying road roughness, and we have used it to define our Thaw settlement criteria. So the localized Thaw settlement, it can contribute to increased IRI. The more IRI you have, the more roughness you are going to have, and your road is going to be less serviceable. So if you have a Thaw settlement at your study site, at your borehole, it's going to increase the IRI. But we had looked at different guidelines, and ASTM recommends a maximum IRI threshold of 25 meters per kilometer for gravel roads. But for northern regions and roads and highways, 25 millimeter per meter, it technically means that you have 25 millimeters of settlement at your location, which is too low because of the size of the trucks and the other factors. So we have defined our Thaw settlement thresholds to be 25 at minimum, 75 and 250 at maximum, and to be able to look at the serviceability of different embankments. So here you're looking at the serviceability plots. From the top, you're looking at the first criteria, 25 millimeter per meter, and the middle one is 75 millimeter per meter, and the last one is 250. And again, the blue lines are the thin embankments and the orange ones are the thick embankments. So all embankments are showing decreasing serviceability over time, obviously, especially under stricter performance thresholds. And it's important to say that the engineers can use these curves to predict how long infrastructure stays functional based on the criteria that they've defined before, and they can use these curves to align the design decisions with real-world ride quality standards like IRI. But I should mention that each line here represents 1,000 simulations for each embankment that we have done. And here you are looking at the optimization plots. So we have done the optimization analysis for just one of the embankments, ITH10. We have chosen it randomly, and we just wanted to showcase our tool and methodology, and we could have done it for any other embankments in our study site. And again, you're looking at the 25 millimeter per meter at top, 75 at the middle, and 250 at the bottom of the figure. And we have defined our serviceability criteria to be 80%. It means that we wanted our embankment to be 80% serviceable at any time, and it's represented by a purple line on each figure. And what are these plots showing us? So the first one at the top is saying that if you want your embankment to be serviceable 80% at a time, and you have a 25 millimeter per meter criteria for Thaw settlement, you should grade it every year. If you have a less strict Thaw settlement criteria, 75, you have to grade it for each 3 years. And if you want it to be serviceable 80% at a time for higher criteria, 250 millimeters, you can grade it every 21 years. But this optimization tool, it provides a decision support mechanism. It allows engineers to plan interventions proactively rather than reactively. It balances performance with maintenance cost, so you should only grade when needed, not too soon or not too late. And it supports long-term financial planning by aligning maintenance schedules with budget and constraints and performance goals. To wrap up, I just want to say that what were our results implications for engineering practice? So as I mentioned, traditional design often rely on single deterministic predictions, and they are blind to worst case scenarios and under or over design. So the work that we have done enables the probabilistic analysis for TEMP. It enables serviceability informed design, and engineers can quantify probability of serviceability loss. It enables tailored maintenance, so optimization of grading intervals reduces cost while keeping service level high. And the scenario-based planning is useful under climate change uncertainty and incomplete data conditions. So I can say that it's not just about predicting Thaw settlement, and it's about managing infrastructure through uncertainty. Thank you so much, and I can take a couple of questions.
Yeah, thank you so much.
That was an interesting talk. Were your simulations in 1D or 2D in TEMP-W? Like, were you simulating the embankment and ground beside, or just the embankment surface in 1D?
Thank you for your question. It was 2D. Yeah, it was the embankment and the lower soil layers. Yeah.
Okay. And then I have a question about the figure on slide 26 where you show the serviceability plots. I'm just wondering why in the 25 millimeter per meter scenario, the thin embankment has a longer service life. Do you have any insight into that? Because, yeah, as it gets to the 250, then it looks like in general, the thick embankment has a longer service life.
Yeah, that's a good question. Actually, in the serviceability analysis that we have done with the criteria and everything that we had, a lot of factors were involved, such as for example, the Thaw strain was really important here. So the differential TLD, yes, that jumped after 2070, by the year 2070, but the Thaw strain had another important effect on the Thaw settlement that we have calculated, and I think it could be because we had a lot of factors, and it just happened after we have done the serviceability analysis. It wasn't only based on the TEMP-W results.
Okay. Can I ask one more quick one? In TEMP-W, were you dynamically moving the surface like as settlement occurred? Or was no, so it was a stable surface?
Yeah, it was just the temperature, yeah.
Yeah, okay, thanks. Thank you very much.
I have a quick follow-up to that, or on the topic of the modeling. I was wondering how long did it take you to run thousands of simulations in TEMP-W, and what was the computing power required for that?
That's a good question. Actually, for the first application, the HBR, we had only one simple sort column, and it took 15 minutes for each simulation. But for the embankments, we had a much bigger simulation, and it took about 25 to 30 minutes for each simulation, which was not that bad. For example, 1,000 simulations for each embankment, it took about, I can say, 2 days maybe. So yeah, it wasn't that bad.
I'd like to thank you again for that wonderful presentation. It's very informative. And everyone, please stay tuned for our next NSERC PermafrostNet seminar. Thank you and have a good day.
Thank you so much.